Welcome back, Advanced Math. This is going to be a video about section 4-6. It may be one video, it may be two videos, I don't know, we'll see how this goes. Every, almost every question in this section can be solved just by using the simple exponential growth and decay model, okay? And then now there are some that might be a little faster to solve a different way. But if you look at it, if I have this formula right here, okay, you've seen this before. This is called the exponential growth model, but it can certainly be used for decay as well. This is A right here, that represents the final amount. This is the initial. E is the number E. R is either the growth rate or the decay rate. So I'm just going to write rate of change. And it's written as a decimal. So if you're if you have a radioactive element that decays away at a rate of 3% per year, that would be negative 0.03 because it's decay. If you have money in a savings account that grows 5% each year, that would be positive 0.05 because it is growing. And then T, of course, is time. So that's called the exponential growth model. Okay, again, you can use it for either a growth or a decay situation. And just a reminder, this is lesson 4-6. And the title, I think, is Modeling with Exponential Functions. Modeling with Exponential Functions. Okay, let us begin. What I've done is I've selected a couple of general problems out of the assignment that we're going to do together, kind of to illustrate how to create a model and then how to use a model to predict the population of birds in the future, how much money you'll have in the future, how long it will take for a radioactive element to decay down to 30% of what it used to be, and so we'll try to do some examples of each type, and then at the end there's actually some problems in here from section 4-7. We don't do that as a separate lesson, but it has to do with different logarithmic scales that are used kind of in the real world. So let's erase this and we'll get started. So if you want to pause the video and open your assignment, the first one we're going to do is actually part of problem number 1. Okay, so just take a second, get that pulled up. Otherwise, I will read it. It says a certain species of bird was introduced into a certain county 25 years ago. Biologists observed that the population doubles every 10 years. And the population is now 27,000. Okay, so these birds were first introduced 25 years ago. There are now 27,000 of them. We know that the population doubles every 10 years. The first question that they ask is this: what was the initial size of the bird population? So in other words, 25 years ago, how many birds were introduced into the county? Well, I know that these birds are growing exponentially. That is the assumption that we make here. So we're going to be able to use the exponential growth model here. Now the only thing is I don't know the growth rate for this exponential model. What I do know is I know how long it takes for the population of birds to double. Okay. I'm going to use the fact that it takes 10 years for the bird population to double. I'm going to use that fact to find our growth rate. Okay. Now, here's how to do it. Anytime you want to find a growth rate, what I have to know is I have to know an initial amount and a final amount and a time period. That way, the only unknown in this model would be the growth rate. All right, so I don't know an initial and a final amount, but I do know that whatever my initial amount, whatever it is, the amount of birds that I start with, it'll take 10 years for it to double. So I can make up whatever initial amount I want to. If I start with 1,000 birds and the population grows to 2,000 birds, I know that that happens over a course of 10 years because that is what was stated in the problem. So what I'll do is I'm just going to put a 1 year and a 2 year. I could just as easily put a 1,000 there and a 2,000 there, or a 1 million here and a 2 million here. The result's going to be the same, and I know that that will take 10 years to happen. Okay, so the only unknown, as you see, is the letter R, which represents the growth rate of the birds. So what I'm going to do is, first of all, I don't really need that 1 there. I can think about dividing both sides by 1. Okay, if I ever have a number there, most of the time what I'll do is I'll divide through by that number before I do anything else. But in this case, of course, if I divide both sides by 1, that 1 just disappears. Now, next I'm going to use some previous knowledge here. I know that anytime I have an unknown that's in an exponent, I'm probably going to use a logarithm to get that unknown down out of the exponent. So I think what I'll do is I'll take the natural log of both sides here. So this side just becomes natural log 2. This side, of course, taking the natural logarithm undoes the exponentiation to base e. So what I end up with then is just r times 10. And then if I divide both sides by 10, I get r equals natural log 2 over 10. Okay, so I found the growth rate for this population of birds. Okay, once I have the growth rate, I have the power to solve whatever problem they throw at us. In this case, it says, and now I'm going to keep, I know I could get a decimal approximation, but I'm just going to leave r like that. That way it's an exact value. Now, what it asked, if you remember, it said, it asked us to find the initial size of the bird population, given that the population right now is 27,000. Okay, so I'm going to erase this. I'm going to remember that that my growth rate is natural log 2 divided by 10. And so when I go to use this model to answer some questions, I know that r is always going to be, for this problem, natural log 2 divided by 10. Now, let me just refresh everybody's memory. Your number may be different than your problem, but it gives us that the population now in my problem is 27,000. So I know that this final amount right now is going to be 27,000. What I don't know is I don't know the initial population of birds. If you remember, that's what they're actually asking us to find, is how many birds were actually introduced to this county 25 years ago. So I'm going to leave that as my unknown A naught. Got an E. I know my value for R is natural log 2 divided by 10 for this problem. And Teddy, will you make sure you can see this on the screen here, please?
Yeah, you can see it.
Thank you. And then my time, it says they were introduced 25 years ago, so that T is going to be a 25. Okay. Now, if you notice, I only have one unknown in this equation, right? And it's the value of A naught, the initial bird population from 25 years ago. So I'm going to solve this for A naught. This is just one number right here, e to the all that business. So I think what I can do is I can just divide through by that number. So I'm going to divide both sides by that quantity right there. So I'm going to get A naught equals 27,000 divided by e to the 25 log 2 all over 10. Okay. Can we still see that, Teddy?
You can't see really the E or the 10 on the bottom.
Is it like in a glare?
Yeah, it's in the glare.
All right, well, all I did was this circled quantity here. I put that under the 27,000. And now I'm going to enter that whole thing into the calculator. That could just be one calculator entry. So I'm going to type in 27,000 and divide that by, I'm going to open a set of parentheses, And I'll use the e to the x function, which remember that's right above your natural log key. And then that's going to be 25 natural log 2, and then divide by 10, close my parentheses there. And I think I've got it correct here. Yeah, okay, so I put my entry in, and what I got was A naught is 4772. That's a 7.97. So I think we can safely round that to 4773 birds, 4,773 birds as our initial population. Now, look, so to recap, all right, we use that exponential growth model. I'll warn you, if you watch like a watch it on here, they might do it a different way. I think it's easier just to do it with this formula, but there are other ways to solve this problem. So what I did was initially I had to use some value for an initial population, some value for a final population over a given time period to find R. Okay. So just know we're always going to be using this, and sometimes I have to substitute in known quantities in order to solve for unknown quantities. Okay, there is a second part to that problem, but I think I'll let you try that on your own. Okay, I am scrolling now, if you still have your assignment here, to number 4, okay? This is a similar problem, and we might not do the whole thing, but I'll let you scroll to number 4 here. And if you're not there yet, it says the population of California was 29.76 million in 1990 and 33.87 million in 2000. And it says the population grows exponentially. Find a function that models the population t years after 1990. So if the population grows exponentially, this will be the model that we use. In order to write the model, okay, this is the model. So if it says find the function that models this is the model, okay? And the answer will be the right-hand side of this equation right here. So it says it models the population in years since 1990. Well, I know the initial population in 1990, it was given to me as 29.76 million. So I'm going to go ahead and do that. I know, well, actually, maybe not. But I'm eventually going to put a 29.76 right there for 29.76 million. Now, what I don't know is I don't know R. I don't know the growth rate. So what I can use is I can use the two populations that they gave me, okay, one from 1990 and one from the year 2000, to solve for the value of R. Because I know that it says the population was 33.87 in 2000 and 29.76 million in 1990, and that's times e to the R. And that to get from this population to this population, it took 10 years, 1990 to 2000. So I'll put a 10 there. And then all I'll have to do there is, again, I recommend to solve for R that we first divide by 29.76. So I'm going to write 33.87 divided by 29.76 equals e to the R times 10. And then, of course, all I have to do to solve for a variable that's in an exponent is to take the natural logarithm of both sides. So I'll get natural log of this side equals natural log of this side. So, of course, natural log cancels with the exponentiation to base e, and I'll get 10r, and r times 10 equals, and this just comes down the way it is. I can divide both sides by 10. I have my value for r. Okay, once I have my value for r, okay, the model's just gonna, it'll be your population in 1990 times e to the r times t. Okay, and in the model it will just be t. Okay, then it says find the time required for the population to double. We've done one like that. Predict the population of California in the year, mine says 2010. You can do that as well. Okay. All right. Let's go to number 5. This is going to deal with a different topic altogether. So I'll give you a second to read number 5. Alright, so this says it uses the radioactive decay model. Well, this works just fine for a decay model too. The only thing is R will be negative because instead of the amount of stuff increasing with time, it's going to decrease with time. So I'm reading this. It says there's 250 milligrams of a radioactive element decays to 190 milligrams in 12 hours. Find the half-life of the element. Okay, half-life. So half-life, you probably most of you are either in chemistry or you've had chemistry in the past. Remember, half-life is the amount of time that it takes a radioactive element to decay to half of its original amount. So, for example, if I had 100 kilograms of a radioactive element, after one half-life, that amount would be cut in half to 50 kilograms. After another half-life, it'd go down to 25. After another half-life, it goes to 12.5. And it just keeps getting cut in half. The amount keeps getting cut in half every half-life. Okay? So, if your half-life is 10 years, after 10 years, you have half of the amount of the radioactive element with which you started. That doesn't mean, if the half-life's 10 years, it doesn't mean the whole life's 20 years, okay? Because you always cut the amount in half that you have in half. Okay? So you cut 100 down to 50, then 50 down to 25, etc., etc. Okay, so let's see what this says. It says 250 milligrams is how much we start with. So I'll put that in the initial amount. Now on my problem, it says it decays to 190 milligrams in 12 hours. Okay, well, that's great. What we need to do is use that to find the half-life, or sorry, not the half-life, yeah, we'll eventually get to the half-life. I need to know the growth rate first. So I'm going to put my growth rate as a variable, and it takes 12 hours to go from 250 milligrams, milligrams, down to 190 milligrams. So I can solve for R pretty easily here. I'll divide by 250, and I'll get 190 over 250 equals e to the 12r. Now I'll take the natural log of both sides. So I get log 190 over 250 equals 12r. I'll divide by 12, and I'm going to get this as a decimal approximation here. So I'm going to type in log of 190 divided by 250, and then I'm going to divide that answer by 12. Log 190 divided by 250, and then divide by 12, and I got R is negative 0.02286 97371, and I'll probably keep all the decimal places for now. All right, now that I know the growth rate, I can find the half-life a couple of different ways. If you look in your textbook or watch it, it's going to show you a shortcut for finding the half-life. I'm going to use that shortcut too, but I'll tell you where it comes from. Now that I know the growth rate, it's easy to find the half-life from using this. It's kind of like finding the doubling time, okay? Except this time I'd start with 2 and end up with 1. Okay, I'd start with 2, end up with 1, and I know the growth rate right here, and I just figure out how much time it takes to go from 2 milligrams down to 1 milligram, and that's my half-life. The shortcut, of course, is this. Log 2 divided by R. Okay, I think I wrote that correctly. And so, and if you look, in the book, it'll probably say ln2, natural log 2 divided by k. R and k mean the same thing. It's the growth rate or the decay rate. And so, if I know R, all I have to do to find the half-life, it takes a natural log of 2 and divide it by R. So that's what I'll do. I'm going to type in log 2 divided by my answer, and I got 30. For my hours. Now, it says negative 30 on here, and that's going to be okay. nearest whole number. Time is always measured in positive units, so that will be a positive answer. Okay, the next, 6 uses the same, 6 is still talking about the radioactive decay model. Let's look. Next one is 11. Okay, so 11. What we're going to have to do for 11 is talk about the pH scale. And again, if you've been in chemistry, you might already know how pH is figured. I'll erase this, and we're not using this exponential growth model anymore. These next problems are just going to be some applications. pH, lowercase p, uppercase h, is the negative log of the hydronium ion H plus. Okay, so whatever the concentration of H plus is, you take the negative log of that, and that gives you your pH. All right, remember, like a pH of 7 is neutral. If you go below 7, that's acidic. If you go above 7, that's base. Okay. So let's see what this says. Sorry, I got off of the problem page here. Okay, so it says find the pH of orange. Mine says oranges. Now it's in red, so you might get something besides oranges. But it says that the concentration of the hydronium ion there is 2.5 times 10 to the negative 4th. So the pH would just be the negative log of 2.5 times 10 to the negative 4th. Okay, and that should just be a calculator entry here. Now, that's in scientific notation. You can change it to standard notation if you're not comfortable with that, typing it into your calculator. But if you don't know how to do that, what you do is it's above the comma key where it says EE. So what I'm going to do is I'm going to type in negative and then the log key, the LOG key, that's a base 10 logarithm. And then I'm going to type 2.5 and then second and then the comma key and then negative 4th. Okay. Hit enter and I got 3.6. So the pH of an orange is 3.6. It's a little bit acidic. Okay, it's the pH is below 7, so oranges are acidic. Okay, that's an example of a logarithmic scale. Okay, the pH of something is the value of the pH is found by using a logarithmic scale. All right, next application is application of decibels. So we're going to do Richter scale first. Okay, so you might remember the Richter scale measures what's called the magnitude of an earthquake. And the magnitude of an earthquake is found by using the intensity of the earthquake. And here's the way it works. So the magnitude, capital M. Okay, Teddy, what's going on?
Nothing.
Oh. Okay. For those viewers at home, somebody just slapped somebody else, so somebody's going to get in trouble when this video is over. Thomas, no crying, boy. Alright, so the magnitude, capital M, is the log of the intensity of the earthquake divided by the intensity of what's called a standard earthquake. Okay, so S is a constant. Alright, S is called the intensity of a standard earthquake. You've seen on TV or movies or something when there's an earthquake, there's like a little, there's paper that goes across the thing and there's a needle and it goes like that. Okay, that is called the readout from a seismograph. And simply the amplitude of those fluctuations gives you the intensity of an earthquake. Okay, like for example, if the amplitude of that was 3 centimeters, we would say the intensity of the earthquake is 3 centimeters. Okay, the standard earthquake has an intensity of 1 micron, which is 1 times 10 to the negative 4th centimeter. So I think that's 1,000th of a centimeter. Okay, So a standard earthquake, it has a very, very, very low intensity. All right, so if I want to know the magnitude of any other earthquake, I just measure its intensity, and I put the intensity right there. Okay. So let's do an example here. I've got an example here. Find the magnitude of an earthquake that has an intensity of 3.75. An intensity of 3.75, just to recap, means that the seismograph reading is going to be, the amplitude is going to be 3.75 centimeters. So what I do is I do this, log of 3.75, and I divide that by the intensity of a standard earthquake. Okay, S, all right, I said it, but I didn't write it down. It's always 10 to the negative fourth centimeters. So I'll write 10 to the negative fourth. Okay, and then I'll calculate that. I'll just type that in.
Dad,
Yeah.
I have to go.
What's that?
I have a Google Meet in like 2 minutes.
Okay, hang on. Just leave it running for me, okay? Alright, so I got that the magnitude here would be 4.57. And it doesn't really have a unit, that's just the magnitude. Okay, now you probably know from experience that's not a terribly big earthquake. Okay, like the largest earthquake I think they've measured is like 8.9. Okay, I don't know if you've there have been any earthquakes, famous earthquakes in your lifetime. The one in San Francisco during the World Series, I think it was 1989, had a 7.1 magnitude. That was pretty big. I mean, you saw like bridges. I mean, not the whole bridge collapse, but like parts of the bridge collapse on top of cars and stuff. It certainly shook up the stadium during the series. Okay, so that's how you use the Richter scale. The Richter scale again is called a logarithmic scale because it uses logarithms. All right, now one last application here, and it's kind of an interesting one. Decibels. So decibels are a measure of loudness. Okay, how loud we perceive a sound to be. Okay, now that's not. Decibels are not a unit that are like in the standard metric system or the standard international system of units. Okay, decibels are the value for the decibel for the loudness of a sound are obtained from what's called the intensity of the sound. So I'll write the formula up here. Okay, so our textbook uses a B for loudness, and that's measured in decibels. It's 10 times the log of the intensity of the sound. Okay, there seems to be some sort of a Google Meet going on in the background. Sorry about that. We'll continue. I'm sorry if that's going to be distracting. All right, so what is I naught? I naught is the sound that is what's considered the threshold for human hearing. So it's the softest sound that the human ear can hear. And I, in this case, is 10 to the negative 12th. And let me talk about the units. The units there are in watts per square meter. Okay, the intensity of sound is measured in watts per square meter. Now, watts, remember, are a unit of power, so that's how much power is flowing through each square meter. Okay, now, well, watt is a joule per second, where joule is a unit of energy. Okay, so how much energy is a joule? Well, not very much. A joule can lift an apple 1 meter. Okay, that's a rough estimate. In 1 gallon of gasoline, there are 120 million joules. Okay, so joule is a very small amount of energy. Okay, and remember, energy is how quickly power flows. Power is how quickly energy flows through something. Okay, and anyway, so that's 10 to the 12th, 10 to the negative 12th watts per square meter. Now, let's think about this for a second, and I'm looking at an example here. It says find the decibel level of a jet engine at takeoff if the intensity is 100 watts per square meter. So to find the decibel level, I take 10 times the log of, and it says 100 watts per square meter, so the intensity is 100, and I divide that by my I naught, which, whoops, I wrote 10 to the negative second, that should be 10 to the negative 12th. And then I just calculate it. Okay, so I type in 10 log of 100 divided by 10 to the negative 12th. And I got 140. Okay, 140 decibels.
30 minutes.
Thank you. Is 140 decibels is pretty loud. Okay, if you've been to an arena where they measure the decibel levels, I remember like at the Hearn Center they had a thing that measured the decibel, how loud the sound was when the crowd would cheer. It could get to about 120. I know Arrowhead's one of the louder stadiums in the world, really. You can look up like what the record sound level is. Okay, now here is something that I'd like you to think about here. 100 watts. Okay, maybe you have a car stereo system. That puts out 100 watts. Or 100 watts is pretty